Tôi không có dùng cái bảng này ha. Tôi thì một vài cái tôi sẽ lecture, okay? Nói tiếng Việt như vậy ha. I want to lecture on blackboard and chalk, okay? And occasionally I will use the computer for demonstration. Is it on? Signal? Processing, right? So the idea here is how to process signal in a more efficient way. And of course, the way you process depends on application. So so far you have seen that there's a lot of way to model this kind of process. So we have input x of n. So I use n here would be the index. Okay, the n take on value of 0, 1, 2, and so on for causal system, and it can be negative also for anti-causal system. Okay, so this is the value for n, and then we model the linear system by an impulse response, x of n. So this is impulse response, x of n, and then we measure the output y of n. So I'm sure that Professor Min have talked about convolution, sum, and so on and so forth. So here we have a summation, you have x of k, x of n minus k, and so on, right? Sum over k. So this is called convolution, and this is how we use to measure or compute the output for a particular system. Okay, so this kind of layout is called analysis, right? Analysis meaning that we are given the system x of n, we're given the input x of n. How do you find the output? That's an analyzing. Okay. The second part, I'm sure when he discussing this, is on the synthesis. Okay, so synthesis is the opposite way. Synthesis, you want a particular output, right? How do you design the filter to achieve that, right? So this is to somehow come up with x of n, right? Analysis, you are given x of n. Okay? So basically I'm trying to spend the first 10 minutes for review and then leading up to my lecture. Okay? So in analysis, what do we use for this? We use convolution. And why we use convolution? Because we have a linear system, linear carbon-invariant system. Okay? And from here, we can show that if you have a exponential signal, e to the j omega naught n, okay? Omega naught is frequency from 0 to pi. Then what is the output? For that particular input, what is the output? The output will be the same as the input, right? What is the weighting factor? The Fourier transform of that system measured at frequency omega naught. Okay, so this is the property of LTI system, and this way we can actually talk about Fourier transform. So the definition of Fourier transform is summation in n, x of n e to the minus j omega naught n, right? And vary omega naught, you can measure the frequency response and so on and so forth. And you can show that using this mapping from time to frequency. Convolution, which is flip, shift, and then we sum together, can be done very efficiently in the frequency domain. Right? So frequency domain, you will have y. Yeah. The most effective way to learn is to ask questions right away. So we can derive in terms of the mapping from time to frequency using this eigen function property is that the output y in frequency is the product, right, of h and x. So this is the important properties of LTI system, is that you can very efficiently compute, instead of convolution, which could be involved, you can do this in frequency domain. So you have a choice between implementing the system in frequency or time. Okay, so when you talk about frequency, then you have all the properties we will review later on. Okay. So there's a lot of ways to look at this equation here, right? Suppose I have, take an example. Suppose my system, okay? Let's say the input response is 1/2, 1/2. So this is time 0 is 1/2, time 1 is 1/2. So who can describe this system for me? What does this do? It's an average, right? Basically, if you take a look at this, plug into here, basically the average of the two successive sequence, right? Okay, you take x of n, so you freeze time, n can be 1. You take 1, you add it with x of 0, you divide by 2. Okay, so this is an average operation. So how do we describe average in frequency domain? How do we describe average in frequency domain? So what do we mean by frequency domain? We have a phase, right? We have a phase and magnitude. Okay, so this is magnitude of h, and this is omega, and here's phase of h in omega. Okay. Who remember the magnitude response of this average? Okay. So what does it look like here? How do I plot this? Circle. Okay. So one way to do this is look at that. What happens at this frequency 0 pi to 2 pi, and it is periodic, right? We know that in the DSP, the frequency are repeat every 2 pi. Okay, so you only have to look at the frequency response for every 2 pi interval. Okay, so what is the magnitude at time 0? At frequency 0, sorry. It's 1, right? Basically, you have this. So at frequency 0, you have 1. At frequency pi, you have 0. So it is a low pass filter. So you can see that the operation in frequency domain is that it is preserving the DC values, right? 0 is DC. The pi is high frequency. It's actually filter out high frequency. And this is we call a low pass filter. Okay? What is the response from pi to 2 pi? The same as this, right? Just like this. Okay? And so on. What is the phase response of this filter?
Line 0.
It is 0? It's a straight line, right? It is a linear phase. Just what is the slope of that line? It's 1/2. Okay, so it's going to be like this, right? It's going to be like that. Okay, it's called linear phase. It's preserving the group phase. Is that okay?